Okay, so I am streaming this live on YouTube, and I'll also record. Okay, so I am streaming this live on YouTube. Okay, so we are all set. There's recording on the cloud, and then the session is live on YouTube. And please feel free to have pizza, and those who haven't signed up, please sign up as well. So I'll start with an introduction to the chapter. This is supposed to be an open house where one of the aims is to attract new members to the chapter. So I will, there'll be a little bit of sales pitch, but I'll keep it short. And then after the state of the chapter, we'll, live transcription. Live transcription is actually, anyway, there is closed captioning, real-time closed captioning, but anyway, I enable it. Let's see how it works. Okay, so we're all good. Okay, so welcome to the IEEE Computer Society Silicon Valley chapter. I'm the chapter chair, Vishnu Pendyala. Just wanted to quickly go over some stuff about the chapter, and hopefully you will, if you are not a member yet, hopefully you will consider becoming a member of IEEE. So this is IEEE at a glance. IEEE is the world's largest technical professional organization for the advancement of technology. So as you can see from the numbers on the screen, there are 400,000 plus members, qualified members, because IEEE doesn't take everyone, I believe, as members. 39 technical societies. Its presence is in 160 plus countries. 1,600 plus conferences, 5 million plus technical documents, 200 plus periodicals, and standards is also one of the main things in the charter of IEEE. So our section is the largest in the world, the Silicon Valley section, and our chapter, at least from the latest information that I have, at least from the information that I have, may not be latest, but from the information that I have, this section is the largest in the world. IEEE itself is the largest professional organization in the world, and our section is the largest in the world within IEEE, and our charter is the largest in the section. So there are a number of benefits of membership. So one thing is you have access to plenty of information and research and valuable networking opportunities. We are slowly opening up. This is the first event after the pandemic when we are meeting live. So we are slowly opening up. So networking is a great thing. You know, a lot of things happen through networking. So that's an advantage, and career and local activities. And more importantly, you have a channel to volunteer, to contribute to the society, to the community. There are a number of opportunities. So that is what interested me, actually. That's number one reason why I wanted to join IEEE, to volunteer mainly. When I was a student itself, that's when it really attracted me. And then the other advantages are also there. There are plenty of member resources. So you have the IEEE Explore, which is a repository of the 5 million plus documents that we talked about, technical documents. Of course, it's paid, so you'll have to pay something extra for that, but it's available. And you have IEEE.tv, where you find really good talks. In fact, this today's session is also likely going to be put up on IEEE.tv. You have proceedings, magazines, journals, and then standards is also very important when it comes to IEEE's chapter. So a quick overview of our events. So far, all our events were online. They were broadcasted live, like today's event on YouTube, and they were later made available on IEEE.tv. All our chapter events are on IEEE.tv. We had some really good speakers and researchers participate in our events, like Professor Pedro Domingos and Bjorn Schuller. They are world-renowned researchers. The topics that we cover are really cutting edge, like Professor Schuller, the Ask Me Anything session was on artificial emotional intelligence. And we are slowly getting back to in-person meetings. The next one is going to be in September in Santa Clara University. The speaker is a senior vice president and general manager of a large networking company. He is currently traveling internationally when I contacted him. So we are going to finalize the program as soon as he is back, I think this week. So please watch out for that. And we have been doing this annual conference called NFIC. It has been largely successful. In the previous years, it was hosted in Stanford University. But after the pandemic, it has been virtual. Last year, there were really very highly reputed speakers. And the program can be checked out on the web as well. And this year, we are going to have it in August. This conference is in partnership with the Taiwanese North American Association, NATIA. So we are still in discussions, but at least we have one confirmed speaker who is a CTO, Chief Technology Officer with IBM. So watch out for that as well. And then we have the annual town hall and open house like we are having today. And we also co-sponsor a number of activities. So one of the leading partners for the chapter is the Corporate Liaison program. So we actually had really solid events there. So one of the events, the speaker was Bill Daly. I think most of you know Bill Daly is the senior vice president with NVIDIA and also a professor with Stanford University. So that was a huge success. And then we also co-sponsored talks on multiple topics like cybersecurity, artificial intelligence solutions. And then coming up is a conference called GHTC. It's a signature conference of IEEE, Global Humanitarian Technology Conference in September, which we are co-sponsoring. And our event, the September event, is co-located with this conference. So, so if you come to that event in September, the chapter event, you might most likely meet a lot of speakers and participants of the conference. And then we have our NFIC, New Frontiers in Computing, in collaboration with NATIA. It's a Taiwanese North American Association. And we have a number of outreach channels, at least according to the 67 participants who registered for this event. Most of them were guided to the registration website through the social media and other websites, other channels. We have our website, which is also pretty popular. It gets a lot of hits, but we also have, we also advertise our events on social media. So please feel free to subscribe. So on Twitter alone, we have 12,400 followers. And our mailing list is also pretty huge. We have more than 4,600 members in the mailing list. And we send out the mailer every month. So please feel free to join if you haven't already. And in terms of memberships, our membership is growing in spite of the pandemic and in spite of the absence of networking opportunities. The membership has been growing. So this information is a little dated, maybe 3 or 4 months before, I think. But pretty much gives, it's a good reflection of the state of the chapter. So we have 43 fellows, up by 5 from the last year, 145 senior members, 757 members, so on and so forth. One thing we are trying to focus on is to increase the participation from both the genders, particularly the female participation. So there's a diversity committee at the section level. We don't have it at the chapter level, but at the section level, they are doing, they are coming up with ways to attract diverse members to our, diverse professionals to our society, to our section and the chapter. So a number of things new that have been introduced this year. So one thing is a chapter magazine called Feed Forward. It's a quarterly magazine. So the first issue included topics from embedded deep learning, Internet of Things, machine learning with robots. And the call for articles is open. So please feel free to contribute. You can visit our website and you'll find the link to submit articles. The next new thing we are introducing is the International Conference on Applied Data Science. It will happen on the 12th of July. It's again on a Tuesday. We have confirmed speakers from India, Romania, United Kingdom, and of course, my talk is also there. I also act as a default speaker. I have many roles. I'm a pizza boy. I am a speaker. I am a chapter chair. I do a lot of stuff for the chapter. So please join this as well. The topics are also pretty exciting, like fuzzy loss functions for generative adversarial networks. We are going to talk about GANs today in today's lecture. So the interesting part is fuzzy logic loss functions. That is the new thing about it. And then learning analytics. Deep learning, we know, plays a big role in machine learning in general, plays a big role in learning. So generating analytics from the education side of things is what Professor Popescu is going to focus on. And then the next generation of artificial intelligence and energy sustainability, Dr. Eigen from UK is going to talk about. And I'm going to talk about deep learning for melodic frameworks, how we used deep learning for particularly Indian classical music. So the other new thing that we introduced this year is the Ask Me Anything series. Like I mentioned, we had a very successful AMA series, AMA session on artificial emotional intelligence with Professor Schuller from Imperial College London. It's available on IEEE TV. And then we have the monthly scholar series webinars, mostly webinars, but maybe the September event is going to be in person. So depending on how the pandemic takes us, where the pandemic takes us, it will be either webinar or in person. But we have covered some really great topics like quantum resistant cryptography, AI for HPC. All these talks have been delivered by really renowned researchers in the world. Embedded heterogeneous computing and blockchain, control systems, sustainability, and of course, machine learning. And we have also introduced this year chapter awards. So you see there, Paul Wessling, he's one of the fellows of our chapter, and he contributes to our chapter extensively. In fact, this room is courtesy Paul Wessling. He arranged the room for us. He's fortunately or unfortunately, because he's vacationing in out of town. But he could not join today in person, but his support is always there. So we recognized him with an award, and the call for awards is still open. So please check out our website. And then we are always in need for volunteers. As I mentioned, I've been taking on multiple roles. So hopefully if more volunteers join, I can reduce my, I can at least involve more people, and it's really satisfying. I mean, I mentioned that I take on many roles, but it is really a satisfying experience. Even when I volunteer as a pizza boy, it's really very satisfying. I ran to Costco, got the pizza. It's still satisfying for me, at least. So there are a number of roles that you can help with. Editorial support, social media publicity, working to bridge, working as a bridge to the student chapters, conference organization, so on and so forth. So if you're interested, please contact me. And so the next event is the half-day virtual conference, ICADS 2022. We have speakers from all over the world again, and hopefully it will be interesting. Any quick questions anyone has? Okay, if nothing, then let's go to the meat of the meeting today's meat of the meeting, which is machine learning, the motor of modernization. So machine learning is becoming increasingly ubiquitous these days, right? I'm pretty sure you all use machine learning at least a few times in a day. Like I use machine learning to log into my laptop, to open my iPhone, to converse with Alexa, or for that matter, Siri. My laptop recognizes my fingerprint using machine learning. iPhone recognizes my face using machine learning. And Alexa or Siri use machine learning for understanding my voice. And these subtitles that you're seeing on the screen are also enabled using machine learning. So there is some amount of machine learning that goes into, that went into preparing these slides as well. I'm pretty sure Microsoft used some machine learning to suggest me this kind of background. This background was suggested by Microsoft PowerPoint. Based on the title, I just type in the title and Microsoft PowerPoint showed me some design ideas, one of which is this. So obviously there is some machine learning going on there as well. But before we delve deeper into machine learning, I want to introduce some guests. So any guesses on who this person is? Anyone has seen this person before? Okay, I'll show you another person. How about this? So these, all your guesses are going to be wrong because these people do not even exist. These are fictitious characters generated by a generative adversarial network. So it's a machine learning framework which generates these images. And you can see how real life, real looking they are. So how do we generate these pictures? It's by playing a guessing game, basically. The programs play a guessing game like people play. But first, for machines to work, everything needs to be in numbers, right? Because machines, you know, they work with binary streams of ones and zeros, bits, right? So everything has to be numbers. So yeah, so these pictures, I got them from this website called thispersondoesnotexist.com, very aptly named. Actually, you can click on this and, oh, this is opening up here. So each time I click, I go to this website, it generates a new face. You can click another, and within no time it generates a new face, which is real looking. So that is the power of machine learning to start with. And so yeah, everything needs to be a number. So an image is, to the machine, the image is a bunch of numbers, right? So you all recognize this famous personality, right? Abraham Lincoln. So to us, he is Abraham Lincoln, but to the machine, it's a bunch of numbers. So what are the numbers? They are the pixel values, right? So to the machine, a face is a matrix of numbers. And what is each row of a matrix called? It's a vector, right? It's a row vector, basically. And what is the study of matrices called? It's linear algebra, because matrices typically represent linear equations, linear system of equations. So it's called linear algebra. So vectors, matrices, and linear algebra are fundamental to machine learning and to the emerging technologies as well, like quantum computing, right? So now back to our problem of how to generate these images, these real looking images. So it's like how we play the game called Akinator. When I was a student, we used to play this a lot. And those days it used to be called Bullseye. I think it may still be called Bullseye in India, where I grew up. So the game is very simple. There's a website for this as well called akinator.com, en.akinator.com. So the Akinator is a genie, and then the genie asks you to think about a real or a fictional character, and the genie is going to guess who it is, right? So I think about a character, and the genie is going to ask me, is this a male or a female? Or rather, the answers have to be in yes or no. So the genie is going to ask me, male, is the person male? Then I'm going to say yes, probably. Then the Akinator is going to ask me, is the person a celebrity? Then I might say yes as well. Then the next question could be, is the person a politician? I would say no. Then the next question could be, is the person a cinema actor? Then I might say yes. Then what is the Akinator might ask questions about the genre of the movies the actor acted, and so on and so forth. And eventually the Akinator is going to guess who the person is in my mind by asking a number of questions. And the answers are yes or no. So a similar thing happens in generative adversarial networks. So another analogy is like how a kid learns to write the alphabet, right? Like I remember the days when I learned the alphabet. It's many years back, but still I remember vaguely. So how my mom taught me how to write the letter A. So she would tell me, I would just in the first instance, I would scribble something like this, some nonsensical scratch on the paper. Then obviously my mom would say, that's not correct. You have to write A. I still remember my mother's words. She said, write one circle followed by a half circle, one full circle followed by a half circle. So that is some feedback that I got. And based on that feedback, I did something which is somewhat closer to A. But still it wouldn't be any close to the real looking A. So I would, after many iterations and after getting feedback in every iteration from my mom, I finally would learn to write A. So that is exactly what happens here. There are two programs here actually. There's a generator and then there's a discriminator. Both of them are machine learning programs. So the generator initially generates noise, just like the little kid generates noise. The generator generates noise, it's complete random noise. And then many attempts later, based on the feedback, the discriminator acts like the parent. Generator acts like the little kid and the discriminator acts like the parent. So just like the little kid improves after many iterations and getting feedback from the parent. So generator gets feedback from the discriminator, and after many attempts, it generates something that is close to a person's face. But the discriminator would still say, no, that is not correct, and pass some feedback to the generator. And eventually, after many attempts, the discriminator is going to say, okay, good, you did a good job, generator. The image that you have generated is a picture of a real person. So the generator basically tricked the discriminator to believe that the generated image is that of a real person. So there are two things happening. So one thing is generating data from random noise. The first attempt is a total random noise, and slowly a real looking face is generated. So that is one part of it. And the other part is adversarial. So the discriminator is acting like an adversary to the generator. I mean, typically they should not be, but parents or teachers are sometimes seen as adversaries, right? Playful students, playful kids. They think of parents or teachers as adversaries, though parents and teachers are actually helping them learn. They consider them as adversaries because the way they keep saying no to things probably is a cause for that. So same thing is happening here. Discriminator is acting like an adversary. So that is the reason why the pair of these programs is called generative adversarial network. So a little more detail. So we all know, just like in the real world situation, parent is already trained, right? The first training happens to the parent. So similarly, the discriminator is trained first. So just like the parent is trained already on how a letter should look like, the discriminator is trained on how a real image should look like. Again, this also happens in a number of iterations. It's not going to learn right away, right? So what happens is that the discriminator is passed two kinds of images. One is fictitious images at the bottom and the real images at the top, right? So, and these images are labeled as real images or fake images. So the data set is already labeled. So based on the this data set, the discriminator learns, and the way it learns is by what is called as a loss mechanism, right? Loss, we all know. I mean, what is loss? Just like when a person buys a car for, say, $10,000, and then as soon as he buys the car in the new state that he arrived at for his job, his boss says that, oh, you have to travel to a different state. He will have to sell the car. So next week he sells the car for $7,000. It's a loss of $3,000, right? So the same concept is here. So the loss is basically the numbers that are expected to be generated by the discriminator, but the discriminator is not going to generate the exact numbers. So the difference between what the discriminator generates and what it is expected to generate is the simplest loss. But an analogy for loss is also the feedback from the teacher, right? The feedback from the teacher to a student. If the teacher is too lenient, the student is not going to learn quickly, right? The rate of learning is slow. If the assignments are just slam dunk and the quizzes are slam dunk, very easy to pass, the student is not likely to learn a lot. It doesn't serve as a good motivation. So same thing with loss functions. Loss functions provide the most important, most needed feedback for the machine learning program to improve. So if the loss function is simple difference between what is expected and what is generated, then it's not enough for the program to actually learn, right? So the loss function, that is the reason why it's called loss function, not just loss, right? So we typically come up with a function to represent the loss, right? So it's slightly involved. But the essence of loss is still the same, the difference between what is expected and what is really output. But it's a little more involved, like simple loss. One of the most often used loss functions is the RMSE, right? Squared error. Instead of just the difference between expected and output, you actually square that difference. So squared error is one of the loss functions which is typically used in machine learning programs. There are several other loss functions also, like now next month's event, the conference, one of the professors is going to talk about fuzzy loss functions, right? The loss function is not only more complicated than just a difference, but it is also fuzzy. That means it's not deterministic. So there's a lot of research in the loss functions area because loss functions, just like the feedback drives learning in human setting, right? The feedback that the professor gives to the students drives the learning in the human setting. Same thing with machine learning, right? The feedback that is given to the program by way of loss functions tells how well the machine should learn, right? So you can think of loss as a lesson, something that is like a feedback, a lesson to learn. The adage goes, right, no gains without pain. So loss represents the pain that the program should take to become better. So the discriminator is trained now. The next turn is for the generator. Again, the generator is trained in iterative fashion. This time the loss is computed by the discriminator, and then that loss is passed to the generator. So the generator goes over a number of iterations and finally learns to generate real looking images based on the loss that is computed in each iteration, right? So this is a schematic for the entire setup. So you have a generator and a discriminator. So these blocks, so what are the, how many numbers does an image have? Like for instance, take a typical resolution of 1920 pixels by 1080 pixels. It's called 1080p, right? So how many numbers are there in that image? How many pixel values? 2 million, right? 2 megabytes typically. 2 million values. So you have to pass 2 million values to this machine learning program, which is substantial, right? So, and then it is wasteful also, right? Why is it wasteful? It is wasteful because the pixels are correlated, right? For instance, the pixel, this is 8, right? So this pixel here and the one below it is, they're correlated, right? If this is going to be black, this is also going to be black, right? Similarly, if this is going to be white, the adjacent pixels will also be white. So they're all correlated. So what is the point in making the machine process 2 million values, which are all correlated, mostly correlated, right? So to reduce the computation, there's a technique called convolution. In math, there is a convolution operator, but it is not the same as the convolution in machine learning. But they have used, I mean, we overuse the terms, right? In computer science, there are so many terms which are overused. just like in object-oriented programming, operator overloading, we overload some terms. So convolution is one such term which is overloaded, but essentially what it means is you're going to combine a bunch of pixels into one value before passing it to the machine learning program. So that's why these boxes represent the convolutions, right? If you look at the discriminator, the image is a big box. Then through the convolutional layers, the size is really reduced to a smaller box. So it's called convolutional neural network. The program is called convolutional neural network. We'll come to neural networks a little later, but it's a machine learning program. Neural network is a machine learning program. So CNNs, as they are called, convolutional neural networks, are commonly used for image processing. So that is the idea of a generative adversarial network. We are going to have a bunch of images which are already labeled, called the training data set. And then we train the discriminator first and then the generator. And then the whole setup is going to generate real looking images. So here's an example of generating handwritten digits. You can see how it is all noise in the beginning, random noise, totally doesn't make sense. And after many, many trials, it's going to improve, and then the numbers are going to look like numbers, handwritten numbers, right? So that's how these handwritten digits are generated using GANs. So this is a phase GAN demo. So it uses actually two GANs. One is called progressive growing GAN, and the other is transparent latent space GAN, TL GAN. So you can actually configure the phase, how much machoism should look in the face, and what are the other things, the hair color and all that stuff. They are configurable. So we'll talk a little more about those kind of GANs, but I wanted to impress you with this movie that is entirely generated by artificial intelligence as well. Or rather, the screenplay, not the movie, but the screenplay. So the screenplay for this movie is entirely generated by artificial intelligence, not just images, but the movie screenplay itself. So, to save time, I'll just...
In my life, it may never be free.
You can see the expressions in the face and all that. So the screenplay is entirely generated by artificial intelligence. So that is the power of machine learning. So in this context, I'm a great fan of quotations, and this quotation is very much applicable to the big data, and particularly using generative models. So what I believe, Richard Feynman is a Nobel laureate. And what he said is, what I cannot create, I do not understand. To understand data, we need to create data. Until we create data, we haven't understood data. So that is the goal of generative models, and generative adversarial networks is an emerging trend in machine learning. In fact, every week, new papers using generative adversarial networks are coming up, and there's a website called on GitHub. There's a GitHub repository which is tracking all these GANs, different types of GANs that are coming up on a daily basis or a weekly basis. And you can see it's exponentially growing. The number of papers in GANs is exponentially growing. And you can see the types of GANs. All these are generative adversarial networks. Hundreds or maybe even thousands. I don't remember the last number, but there are thousands of GANs. So there's a whole zoo out there that you can explore. So I explored one animal in the zoo with my students. And that experiment is in music, but we use this paper on CycleGAN. Oh, sorry, I'm not showing it. So this paper is on CycleGAN. So the original CycleGAN paper, which I'm showing on the screen, was used to convert between similar looking images. For instance, in this case, horse to zebra. So for that kind of a problem, we typically need several paired examples in the training data set, right? We need an image of horse, and then we need an image of zebra, which corresponds to the horse. And then we need to tell them program that, okay, this horse corresponds to this zebra. But that's a very expensive operation. I mean, how are you going to find a number of horses and then equivalent zebras which look exactly like the horse? It's a challenge, right? Paired images is a big challenge, collecting data set of a pair of paired examples. So that is where CycleGANs help. So CycleGANs do not require paired images. You can collect any images of horses and any other set of images for the zebras, dump them together into the program, and the CycleGAN is going to figure out the similarities, right? So the loss, it is still based on losses, loss function, but the loss that is computed here is cycle loss. We'll talk about the concepts in the next slide, but this is still based on generative adversarial networks. And because of the cyclic operation, it's called cycle consistent adversarial network. So this is the basic idea of CycleGAN. And if you try to think how this is happening, what the CycleGAN program is essentially doing is trying to get hidden latent features of both the horses and the zebras. See, I'll give you a simple example. Suppose you are given a normal distribution with mean some number x1 and the standard deviation x2. Can you generate another number which conforms to that distribution? You can, right? You know probability distributions. You know the parameters of a probability distribution. You will be able to generate any number of numbers conforming to that distribution. The same thing is happening in this example in machine learning. One kind of machine learning, we try to find the real hidden parameters, the latent features of the data. And then once we know those latent features, we can generate any amount of data which conforms to those features. So we use CycleGAN for one of my interests, which is Indian classical music. When I've been trying to learn Indian classical music since my childhood, but in vain for various reasons, time being one of them. But the interest doesn't die, right? I mean, it's inborn. So I use machine learning for music. My latest paper is also on applying deep learning for music. We use CycleGAN to convert a melodic framework. In Indian music, it's called raga. There are two styles of melodic frameworks in India. One is the North Indian style, which has influence from the Mughals and the Middle East. And then there's the South Indian style as well. So we use CycleGAN to see if we can convert a melodic framework in the North Indian style to a melodic framework in the South Indian style. So as you can see here, cycle GAN, this whole setup is called a cycle GAN. Cycle because there's a loop, and then GAN because it's a generative adversarial network, a pair of GANs actually. So cycle GANs have a pair of generators and discriminator. Here we see the first pair in pink and the second generator discriminator pair in green. The first pair works to convert music in a North Indian raga. It's the melodic framework is called Bhairavi, to a South Indian melodic framework called Shanmukha Priya. And the second pair does the opposite. So the generator discriminator pair works just like before, just that instead of random noise to start with, the generator starts with a real note, a musical note. So we input original music notes in the North Indian melodic framework, which is Bhairavi. As you can see, the original samples are shown in yellow. These are the original music snippets in both North Indian and South Indian styles, right? So simple loss or simple adversarial loss, like in the generative adversarial networks, is not enough. So we compute cycle consistency loss to determine how different the generated raga is from the original raga. So we start with this North Indian raga. The thick lines, yeah.
I was wondering, are there people who is there human intelligence that indicates that what you're trying to do is feasible? Are there people who know North Indian style in their brains, South Indian style?
Yes.
Thank you.
Yes. Yeah. In fact, in the previous example, this is a good example, right? We are all human beings, and we are able to tell that the horse is really looking like the zebra, right? So that human discernment is always possible. So in fact, for this project, we talked to a bunch of musicians as well. And it was a small snippet, so it wasn't very, the musician could not thoroughly say that, okay, this is conforms to this raga, but it was close. He agreed that it was close. One of the musicians agreed that it was close. But yeah, the human discernment was there. So, the cycle basically is shown in arrows. The thick arrows denote the transfer from the North Indian raga to South Indian raga, and the thin arrows or the regular arrows show the other way around, right? So, what happens is you pass this North Indian music in Rag Bhairavi to the first generator. It produces, based on the feedback from the discriminator, it produces the South Indian raga, right? And that in turn is passed to the second generator, and that converts to the North Indian raga back. So our goal is for this music snippet to match the original music snippet because it has gone through the cycle. But obviously it will not, because it's a program. It's not perfect. Machine learning programs are not perfect. So there's a loss. There's a difference in what is expected and what is computed. And that loss is called a cycle consistency loss. This is what is used to improve the whole process, right? So the GANs basically bring together two powerful paradigms which are often used. One is the deep generative models, and the other is the adversarial learning. So there's a lot of promise here. In fact, GANs have proven to be much better than some of the older models. And this is the way going forward. So this is from a paper that we published with 2 of my undergrad students who did all the experiments. And we published it in Springer Proceedings. So this is music generated by artificial intelligence. So So IVA, Artificial Intelligence Virtual Artist, is an artificial intelligence composing soundtrack music. So I believe it's from NVIDIA. You can try it out actually. There's a website called AIVA, Artificial Intelligence Virtual Artist. Actually, maybe I can click. But anyway, you can try it out, aiva.ai. And the music is all produced by artificial intelligence. And machine learning is one of the, when I was a student of artificial intelligence, machine learning was a very small component of artificial intelligence. But today, machine learning and artificial intelligence are more or less synonymous. They're used almost interchangeably. So that is how much machine learning has grown in these years. So hopefully you are now convinced that machine learning is the motor of modernization. A lot of modernization is happening by way of modernization, and it is driving innovation. In fact, it is driving the progress of civilization itself. And machine learning will continue to be a key economic driver, right? Google is entirely powered, mostly powered by machine learning, right? And you know the market cap of Google. For that matter, most of these top companies, the economy is, which are driving the economy, they are being powered by machine learning, essentially. So I don't know how many of you have noticed, Google searches have improved tremendously in the last 4 or 5 years. It's because of machine learning, a framework, machine learning framework called BERT that Google invented. It's a natural language processing framework. So it is really an exciting time to be working in this area. So some of the key concepts, right? First thing to note is machine learning is a paradigm shift, right? There are a lot of new things happening in machine learning. So in the traditional programming, we looked at limited data. For instance, we looked at personal characteristics of one person. So analyze one person, and then we model the behavior of that one person. I'm just giving an example, but an easy example to understand. But traditional programming goes a lot more beyond this simple example. But the essential idea was to analyze limited data and come up with a behavior for that data. So in this case, if the person X is polite, magnanimous, and all that stuff, good stuff, then the person we classify as good, otherwise bad or not good or whatever. So that is the traditional programming way. So we generate this model from one person and apply it to everyone. So whenever a new person comes, we are going to check, let the person pass through this code in the left, and then see if the person is good or bad, right? That is typically what we did in traditional programming. So we model a behavior using if-else constructs and loops and apply it to all. But in machine learning, it's the other way around. We analyze many and then apply to one. So we analyze a whole lot of population of data. Could be people, could be customers, could be anything. We analyze many people, and then from the observations that we make by analyzing many, we apply to one. So there's a new person coming in. This person is 90% of the time polite, 83% of the time magnanimous. Is this person good or bad? Is the question that the machine learning program answers. So we are actually flipping the problem around from personalization to generalization to personalization. So the left side is called the training data. The whole big bunch of population that we are going to analyze is called the training data. And the limited data that we are going to apply this behavior to is called the test data. So in traditional machine learning, training data is essentially a table of numbers. Everything has to be numbers for machines to work on, right? So it's a table of numbers. So the rows are instances. So the instances could be those of people, customers, emails, tweets, houses, any other items. So each row represents that instance. So for instance, you want to predict the income of a person or the price of a house, for instance. Let us take the example of price of a person, of a house, right? So each row is a house in that area, and this Y is the price of the house. So those are the rows. And what are the columns? The columns are the features of those instances. So the first feature of the house could be the number of bedrooms. The second feature could be, what do you call that, flooring, whether it's carpeted or whatever. So, and then the roofing, shingles or whatever. So all those are features, right? So the columns represent the features and the rows represent the instances. The last column is a classification category, like good or bad. If it is, we are considering whether the person is good or bad, Y will be either good or bad. But in this case of a house, it will be the price of a house. It's a real number, right? It could be either classes or a real number. Both are possible in machine learning. So here, what we are doing is we are collecting data, and we are also given the resulting values for the data. So we have a bunch of houses, and then we already are given the prices of those houses. We need this Y column also in one kind of learning. So we are given data and the results for that data. From that set, we are going to generate a program or a model, right? But one thing is important. The features should correlate, should somehow determine Y. There should be a relation between Y and the X's. So if X is not related to Y, it's not going to contribute to predicting the value of Y, right? Suppose there's a completely irrelevant feature, like say the social security number of a person. It does not tell you in any way whether the person is good or bad, right? If one of the features or the columns or features, they mean the same. If one of the columns is social security number, it's not going to help, right? So we want all the X's, the features, to be somehow able to determine the value of Y. So that is an important thing. So based on this kind of data set, we are going to generate a model, which is like our program in the traditional programming. And then we are going to apply that model or program on one data item or two data items, which is called the test data. In this test data, Y is not observed. Y, we don't know the value of Y. We are predicting the value of Y. So in this case, the X1 is 90%, 90, X2 is 83, so on and so forth. What is the value of Y is what we are going to predict. So here, data and the results are used to generate the program to predict the behavior of a new item. And the last column is the result, right? So, so another important concept in machine learning is, we all know that this is a vector, right? Each row can be thought of as a row vector, right? You can think of the numbers from x1 to xn in each row as a feature vector. It is a vector because it's a series of numbers, and it is a feature vector because those numbers represent the features, right? So each this part of the row, the first axis part of the row, is a feature vector, right? So that is the other way to look at it. Now, a very important thing to note here is that vector has two interpretations. In mathematics, vectors have two interpretations. So one interpretation is, of course, a series of numbers. Does anyone know what is the other interpretation? A vector. So the other interpretation is a point in space with both magnitude and direction, right? A vector. So if you look at the search for vector here, it is, if you search for vector, vector math, maybe this will. So if you look at the results when we search for vector math, you will see images like this, right? So it's geometrical. It's not numbers, but it's actually geometric. So vectors have two interpretations. One is as a series of numbers, single row or column of numbers. The other is as a point in space with both direction and magnitude, right? So this is a very important concept that we are going to use. So in fact, machine learning relies heavily on this happy marriage of algebra with geometry. So most of the machine learning algorithms are based on that concept of the combining or the coming together of algebra and geometry. So each instance, it could be a person, house, email, whatever you're trying to study. It is actually a point in space with both magnitude and direction. So if it is about a class of students, then each student is a point in space with magnitude and direction, right? So that is an important thing in machine learning. Now, another thing to note is the role of features. So there are a bunch of features, right? For instance, for the predicting the price of a house, the features could be the number of bedrooms, the carpet, the type of carpets, the type of roof, so on and so forth. So a general question, a common question is, will all these features play equally important role in determining the price of a house? Probably no, right? I mean, why are you going to care? So the number of bedrooms probably plays a major role, right? Compared to, say, the type of carpet, right? I mean, I can change my carpet. I don't care for the carpet, right? I can always get in, but number of bedrooms probably will have a higher weight. So each of these features typically do not have the same weight, same level of importance. In any machine learning problem, typically the features do not have the same weight. So you take the example of students also, right? You want to predict the success rate of students. So the features that you study from the student data are not equally important. Sometimes hard work plays, for some subjects, hard work plays a better role than IQ. For some other subjects like machine learning, analytical skills play a better role, bigger role than say hard work. So things like that. So in most of the settings, the features are not equally important. They're unequally important. Yes.
Are the coefficients assumed to be linear, or is that part of how machine learning differs from its predecessors?
Yeah, that's a very good question, and it's a leading question as well. The question is there, can we assume linearity with the data all the time, right? So that is not always true. In fact, for most of the data, linearity doesn't apply. So a lot of machine learning, at least advanced machine learning, is based on non-linearity. So in fact, the distances, if it is linear data, then distances between 2 points, 2 instances, can be computed using Euclidean formula, right? Euclidean distance, the typical Euclidean distance. But if the points are not in a nonlinear space, non-linearly correlated, in a nonlinear space, you'll have to use different metrics. So there's something called geodesic. It's an active area of research. But yeah, typically for advanced machine learning algorithms, at least linearity does not apply. But there are a lot of problems which are linear as well, or at least we assume that they are linear and use some simplistic machine learning models, and still are able to get very good results. Yeah. So yeah, that is the surprising finding in machine learning. We assume some drastic things, but we still get reasonably good success rate. Yeah. So another very simplistic assumption is that these features are all independent of each other, which is not true, right? But still we assume that, and still we get sufficient success rate using some machine learning algorithms. So this model,
still convert coefficients, still whatever we are going to optimize to, we'll still find the right solution.
yes. So that is the essence of machine learning, basically finding the coefficients or the weights, right? Each feature has to be weighed, right? Finding the weights for these features is what this model is. In fact, the model simply comprises of the weights for each of these features for most of the models, machine learning algorithms. So, so yeah, model is essentially the weights given to the features. Once you determine the weights for the features, you can apply, you can do things. So contrast this to the traditional programming. In traditional programming, we had data, like in this simple program, you can see that there's data and then there's program, which will give a result, right? So data plus program is equal to result in traditional programming. Contrast that with machine learning. In machine learning, we are going to provide data. Data is of course needed for everything, but the result also is provided along with the data in machine learning. So we provide the data and the result, and then generate the program. So it's a paradigm shift. Sorry. So it's a complete paradigm shift.
Can you say that if there's no data, you cannot have machine learning?
So that's also a very good question. In fact, it's a leading question as well, because it's a hot research topic. So there is what is called as, yeah, you're right, machine learning requires huge amounts of data, typically. But getting data is very difficult. I mean, some house prices and all that is easy, but for some advanced applications, for instance, self-driving car. The self-driving car is going on the street, and then there is a completely new object which comes in front of it, which is never observed. Self-driving car cannot say, oh, I never observed this, let me go and crash into it, right? It's not, that's not going to help. So there's something called as zero-shot learning, learning without any data. So that's an active area of research. One-shot learning, zero-shot learning, few-shot learning. Few-shot learning is learning with very limited data. One-shot learning is like learning with just one item, data item.
So that's a lot of babies with one shot data.
Exactly. That is what we are trying to simulate. So like a baby is able to recognize a cat, a new cat that comes in just in a single shot, right? So we want to simulate that, the human brain, that aspect of the human brain in using machine learning. So that's an active area of research. But yeah, typically data is needed, and a whole lot of data. If it is deep learning, then you need a whole lot of data. So yeah, that is one paradigm shift. And the most important paradigm shift is deductive versus inductive. In traditional programming, the programs were deductive in nature. So we had if then else rules, iterations, loops, programming constructs, and using all those, we deduced conclusions. We came to conclusions, right? If somebody is like this, something is like that, then this is what we conclude. So that was traditional programming. In machine learning, it's inductive, it's not deductive. So we analyze the population, we model the characteristics, and we apply the model to new samples to induce behavior. Right? It's like how mathematical induction works, right? If it is true for 1, if it is true for 2, then if it is true for n and n plus 1, it is true for every data, all the numbers, right? So induction, it's an inductive approach. So that is what machine learning does. It's completely inductive. And in traditional programming, you measure the code in millions of lines of code, mlogs, right? But in machine learning, it is very much in line with the low code, no code approach that is popular these days. The trend in software industry is for low code, no code. We don't want our employees to work hard and write code, and so we want to make it easy for them. So low code, no code is a revolution that's going on in the software industry, and machine learning falls in line with that. I'll show you in the next slide how simple the code looks like in machine learning. In fact, you don't even need any code for doing machine learning.
Let me ask a question like this. Let's say you have a function written the language, and then let's say you feed lots of random numbers to the input parameters and take the output parameters and generate a network to learn what that function is doing. Is something like that being done? Let's say there's a square root function, input is 1 parameter, output is 1 parameter. Can you generate a network that will basically produce the square root in a meaningful way?
That's a very good question again. So the question is, given a function like computing the square root, there's a program which computes the square root. So the question is whether that function can be implemented in using machine learning techniques, right? So that's a very good question, because artificial neural networks, one of the machine learning programs called artificial neural networks, is known as universal function approximator. So that means you can approximate any function, any function's behavior using neural networks. So it could be square root, it could be a complex function. In fact, there is a paper which uses neural networks to compute to solve differential equations. So it's a universal function approximator. So any function can be approximated. So that is the power of deep learning, right? Deep learning uses artificial neural networks. Just one type of one type of machine learning model called framework called artificial neural networks. Yes.
Is this work being mostly done out of the School of Engineering, or there are plenty of people in the math department also looking at this stuff, so they know all of the corner cases as well?
So that's also a very good question. So the question is whether this study of machine learning is limited to just engineering schools, or it applies to both other schools like math and probably computer science and other areas. So that's a very good question. Actually, we have a professor from computer science department as well here. He can speak to it, but would you?
As a matter of fact, our new data science program in computer science involves math, involves input. So it's a joint program between the math department and computer science department, and a little bit of engineering too. So all three aspects combined together. So yeah, math is very important.
But I think the question there is, as engineers, we approximate things, and we can create some machine learning layer which can sort of get square root of a number. When you look at it from more theoretical math background, we understand the bounds of it, that this is exactly what we are doing. Whatever that is created here is actually because of this model or this relationship, whatever that relationship is.
It is an active area of research. So for instance, you can train a self-driving car to avoid cats, dogs, horses, and so on. But do you really know when you put it on the road, when it sees something that it hasn't been trained on, does it know to stop? And that's one of the limits that I think machine learning has. With expert systems, you can see in the rule base, yeah, you didn't have a rule that said stop if you see this type of animal. But with machine learning, you really don't know what the trained machine can learn. It's just like a child, right? You try to train the child, but yet, are you really sure it knows everything?
Thank you. So yes, another question?
Is there, has the field advanced enough so that we can apply a formula or set of data and say, this we can write traditionally, write code for, and we can look for, and this we need to. Is there an understanding of where that lies?
Okay, the question is if there is an understanding of the divide between where to apply traditional programming and where to apply machine learning. So yeah, I think so. This slide particularly tells you when we can use traditional programming, right? So when there is a deductive nature of the problem's nature is deductive. When we want deterministic results with 100% accuracy and things like that, we use traditional programming. In machine learning, 100% accuracy is a myth. It never happens. So machine learning is more approximate reasoning.
Well, thank you for that answer. But what I was looking at is something like, is there a statement about means and standard deviation that apply to a data set that allow you to say, oh, if we work hard enough, we can write a program that does everything we want. Or conversely, we have to accept the inherent inaccuracy of the problem. Is there basically an epistemological understanding of when the data is this fuzzy, or this chaotic, or this fractal, traditional programming can't come close. It can't solve the problem.
Traditional programming has the same problem. You cannot solve the problem. You cannot anticipate.
Yes, but there's a whole bunch of engineering which is about teaching kids a bunch of techniques we know the answer, the closed form answer of this solution problem. Then there's another set of problems where we say we don't know the closed form, but we have mathematical techniques that make it deterministic enough because we can specify the mean and the variance. A lot of those things in computing are about real time or time bounded response, right?
Yeah.
Then there's the question of, okay, we're happy with sort of any good answer because this is a great way of analyzing a chaotic system or a fractal system or something else like that, right? Because, and what we want is we want insights into the problem so we know what to tweak because we're basically in the position of fixing the airplane while we're flying. And there's a whole bunch of problems for which this seems to be the only answer.
Yeah, that's right. So I think there are some answers in your question itself.
Okay.
So like you talked about closed form, the existence of a closed form solution. And so those are all some of the characteristics that belong to the traditional programming.
Yes.
And the inductive nature of problems and inductive nature of approximate nature of problems. So that's where machine learning can be applied. So, so for instance, okay, I'll give you another example, right? So going back to the previous question, right? Square root. You can write a square root to compute the square root using traditional programming.
Yes.
And traditional programming is likely to produce better results for square root function than machine learning because machine learning is just approximation. So it can be done, square root can be computed using both traditional and machine learning, right?
Yes.
But we would obviously use traditional because first thing is it is simple to implement,
Yes.
right? We don't want to go the machine learning way and do a lot of things to just do a simple square root, right? So I think the intuition is there, where to apply traditional programming and where to apply machine learning. And some of the points on this slide are kind of those guidelines.
Okay.
Yeah. So like if the nature of the problem is more deductive, then we go with traditional programming. If it is inductive, machine learning. If there's a lot of data that needs to be analyzed, we go with machine learning, and so on and so forth. So the big thing in deductive programming or traditional programming is the tooling ecosystem. Of course, tools play an important role in machine learning as well. But most of the software engineering tasks are related to static analysis, debugging, and using a whole ecosystem of tools. In machine learning, the predominant activity is feature engineering, extracting the features from the data. So you're analyzing, the problem is to predict the price of a house. So you are trying to analyze the data to get the features. What features in the data help us to predict the price of a house? That is called feature engineering. That's a very important thing, and it requires some domain knowledge. I mean, domain knowledge played an important role in artificial intelligence, even traditional artificial intelligence. Like expert systems was totally based on domain knowledge. So even today, domain knowledge plays a big role in machine learning as well. And the other big thing in machine learning is hyperparameter tuning, right? So there are what are called hyperparameters, which need to be determined by the people, by the programmers, not by the machines. The weights can be determined programmatically, but the eventual hyperparameters need to be determined by the programmer. Like the number of neurons in neural networks, the number of neurons is a hyperparameter. How many neurons would you want in your network is a hyperparameter. So those things have to be determined by the people. So hyperparameter tuning, I mean, there is some help from the machines, but eventually the decision is that of the programmer. And the traditional programming was code intensive, right? Writing tons of lines of code. And in machine learning, it is more data intensive. You work with gigabytes of data typically. And traditional programming, there's the famous book in traditional programming by Donald Knuth. It's called The Art of Programming. It had some series of volumes. It's like a Bible. I mean,
I look at that book as more like science of programming.
I agree. I agree. I mean, he has written it like a science of programming, but programming is really an art, right? I believe that programming is really an art because I had colleagues who had no formal training in computer science or software, but were excellent programmers for many years. That is because programming has been an art for a long time. Whereas machine learning, on the other hand, is a data science. It's a science. It is based on solid theoretical and math foundations. I mean, computer science itself is applied math. In fact, most of the computer science departments are clubbed with the math departments, but machine learning is more so, right? So those are some of the differences I could quickly come up with. And then this is the most interesting part, right? The whole.
I would like to traditional programming. Maybe most of the practitioners are approaching it from art point of view, but
yes,
it's really a science itself. When you say data science and art of programming, it kind of diminishes the value of traditional programming. Yeah, so I would not accept that.
yeah, I agree. I mean, I kind of agree with it, but it's a bit debate. So the comment is, I don't know if the microphones work well, but the comment is that it's a bit derogatory or diminishing to call programming as an art. It's really a science. I tend to agree. I mean, that debate is always there, right? For instance, management, you call it a science or an art. I believe that management is to a great extent art. I have an MBA in finance, and I am telling you, management is still an art. With any number of amount of study, you may not be able to perfect management. It's really a skill that needs to develop with time, right? The intuition, nothing can cover the intuition that is required for management. So it's debatable, but yeah, your comment is well taken. And this slide is the most interesting, right? So the whole semester long course is just in one slide, this one slide. You can see the amount of code that goes into writing machine learning programs. So the top part is the different machine learning algorithms, which are typically taught in a semester semester long course. K-nearest neighbors, support vector machines, Gaussian process and decision trees and all those things. Those are all different machine learning algorithms. And then you iterate over those algorithms using just 2 lines, because this plotting is just for visualization kind of thing. But just 2 lines. One is to fit the model to the given training data set, and the other is to evaluate the accuracy with the test data set. That's it. This 1 line generates the model, just 1 line.
Oh, wow.
So that is the power of machine learning algorithms, right? Compared to if you had to write the same code in traditional programming, it would take forever probably.
Mm-hmm.
So how does a typical machine learning task look? So first is the toughest challenge, which is to collect the training data, right? So ground truth is like the frame of reference. Collecting the ground truth or the training data is really a challenge, because it serves like the frame of reference. Just like the model apartment that the apartment management shows to help us learn about the remaining apartments, right? So just like that, we need some data which is a frame of reference. So that is a very big challenge, because I mean, just getting the data is fine, but the labels, the Y column that we come up with is the challenge.
programming. If it has not been tested for a case, you don't know how it's going to behave. Same way with the machine learning. If you don't feed the data, you don't know how it is going to behave for unknown data. The same story.
Yeah, so the question is in traditional programming as well, if you don't know, there's a data which is totally new, we are still in doubt. And in machine learning also same thing happens. So how is it different? Does that summarize your question?
At least with traditional programming, you knew how it would perform in non-cancer. But with machine learning, it's a black box. You don't know what the logic inside is.
Yeah, that's a good question. In traditional programming, we know how exactly we came to that conclusion because there's a deduction process involved. But in machine learning, it's an inductive process, and we don't know how exactly things happen. That is a very good question. All these are really excellent questions, but they are all leading questions because this is an active area of research. Most of the questions that you're asking are active areas of research. And your question relates to the explainability of machine learning algorithms, which is also an active area of research. People are trying to build explainable AI. Because suppose you take result from a machine learning program to the court for whatever reasons, facial detection, right? Facial detection is a very important thing. The court may not believe. I mean, how do you conclude that this person is this? There's no solid reasoning. So explainable AI is a very active area of research. So coming up with models which can explain themselves is an active area of research. Yeah, thanks for those questions. So coming back to our machine learning task, so the toughest challenge is annotating the data, coming up with the training data, labeling. For instance, my PhD research was on veracity of data, right? So determining the truthfulness of data. Say Twitter, there are so many tweets. How do you determine the truthfulness of data? So for that, you need some training data, which is already labeled. You need at least 10,000, 20,000 tweets, which are already labeled as true or false. So you take medical domain, right? The pandemic, there are so many rumors floating and all. So for those kind of medical domain kind of important problems, you really need experts to determine whether it is true or false. Each tweet is true or false, right? Because it could cause a panic reaction. If a false tweet can cause a panic reaction. So you need really solid expertise in the area to determine whether it is true or false, which is very expensive. I mean, doctors we know are paid like, for engineers are probably the least paid. Doctors are paid maybe 3 or 4 times more than the engineers, right? They have a larger than life image in the society. So getting medical professionals to annotate is an expensive process, right? So that is the reason why I call it the toughest challenge, is to collect training data. That's the most difficult task in the entire machine learning stack. The next is to extract features. The next step is to extract, not the challenge, but the step is to extract features. So we need some domain knowledge. We need to understand what, for instance, take the example of predicting the house price. We need to know some domain knowledge of a realtor, right? Like we need to know how the type of carpet impacts the price of the house. So we need that kind of domain knowledge. So extracting features is the next step. And then we need to learn the model. So learning the model is essentially computing those different weights for the features, right? There are a bunch of features and we need to learn the weights for the features. Most of the machine learning models depend on that, learning the relative importance of the features. So that is where the machine learning algorithms come into picture, the learning part. And then the validation part. We obviously will not get 100% accuracy because everything is approximation. Is accuracy enough for us? So if it is determining whether Donald Trump, a lot of my students do this project on determining whether somebody's tweets are true or false. Political tweets. They are important, but not as important as, say, the medical tweets, right? Pandemic can cause a whole lot of havoc if they are false. So for political tweets, maybe 70% accuracy is good enough, or 80% accuracy is good enough. But for health-related tweets, we want 98, 99%. So we apply the model. So what we do is, in the validation process, we divide the data into two. The training data set that we collected, we are going to divide it into two. Let me see. Yeah, this one. So we are going to divide the rows into two parts. Maybe the first 70, randomly, 70% of the data, 70% of the rows we'll use for training the model, and the remaining 30% we'll use for validation or test as a test data. So what we basically do is, for the validation data, we are going to close the result. So just like how students learn, right? So they don't look at the answers at the back of the text. The answers are already there, but they are not going to look at the answers first. They are going to take solve the problems without looking at the answers first, and then compare the answers, how well they did. The same thing happens in machine learning. So this 30% of the rows, we are going to cover the results and ask the machine learning program to treat these 30% of the rows as test data, and then determine the result. Then we compare the predicted result with the actual result, just like the students do, to determine the accuracy, how well the program did. So that is what happens in validation, the validation phase. So that's how we are going to determine the accuracy. We evaluate the accuracy. And then if the accuracy is not to the satisfaction, we tune the model. How do we tune? We have a bunch of hyperparameters, like in artificial networks, the number of neurons or the number of layers of neurons. Those are all hyperparameters. We tune those parameters to make the model better. Or if the algorithm, like the point that was made previously, if the data is not linear and we are trying to apply a linear model, the accuracy will be some 50%, 60% or something like that. So in such case, we know linear models will not work well. So we are going to switch to nonlinear models. So all that happens in the validation cycle. So this is a loop, basically. You can see the arrow here. It's a loop. So we need to keep on refining the models. So insights into building the model. So yes.
Are you including data cleansing as part of data gathering?
Yeah, that's a very good question also. Data cleansing is very important for machine learning. In fact, 70% of the time, machine learning projects time is spent for pre-processing the data. And that includes cleaning the data, normalizing the data, and doing all sorts of things. So data pre-processing, cleansing, which includes cleansing, is an important part of machine learning. I did not put it there because I didn't want to confuse the audience with too many details, but yeah, that is a very important step.
In the same labeling the data is crucial, right? If something wrong, it's going to infer.
Exactly. So that is why it's a challenge. The question is, the comment is that labeling data, if the label is incorrect, then the model is incorrect, right? And the model performance will also not be satisfactory. So yeah, labeling is a very important aspect, and that is why it is very expensive as well. So, so how is the model built, basically? The machine learning algorithm tries to find patterns in the data. For instance, in all the training data set that is there, say, for instance, take the example of Twitter, right? Tweets. you have the number of likes, number of retweets, number of favorite, and all those features, right? So what are some of the patterns that we could observe? The patterns could be that the number of retweets is not a very strong predictor of the truthfulness. For instance, there was a tsunami in South India, and there were a lot of retweets of false information. So if your data set is that, then retweets will play a very low role. So that is one pattern. So in other data set, probably the number of retweets really indicates the number of the truthfulness of the tweet. So it all depends on the data set. So, but the idea is to search for those kind of patterns in the data collected as a training data set. So based on those patterns, we determine the weights for each features, right? And then the test data is classified based on the weights. The weights are basically the model, right? Once you get the weights, you can throw away the data. You can even, you just need the model to apply to the test data. And the bigger the data, the higher the chances of precise results. So here's a very simple algorithm. The first class, typically the first class is introduction, but the second class I typically teach this algorithm called logistic regression. So here you can see that the features x1, x2, x3, these are all the features, the columns in the training data, right? These features are given to a summation box. And each feature has to be combined with a weight. So each feature has a different weight. We combine the features, values of the features with the weights. But so this assumes that there's a linear relationship. If you see the formula here, sigma wi xi. So this is the xi is a feature vector, right? This whole thing is a feature vector. This corresponds to one row in the training data set. So feature vector, xi is a feature vector, and wi is a weight vector. So the weights for each of those features. You combine them together. I mean, weighted sum is not an unusual thing, right? In physics, chemistry, we have used weighted sums, weighted averages and weighted sums. So we do the same thing here. We combine the features with the weights and come up with the weighted average. There is a W0 term. So that is the feature for that is 1. So the W0 term indicates the inherent bias in the system. So what is bias? In real world, what is bias? Bias stems from assumptions, right? Simplistic assumptions. Like we assume that one gender performs better. Like there's a gender discrimination suit that was settled a couple of days back with Google, I think, right? So there is a simplistic assumption that one gender performs one way and the other gender performs the other way. Similarly, age bias. So there's a simplistic assumption that certain ages cannot do certain things. So these are simplistic assumptions which result in bias. So same thing in machine learning. So there are simplistic assumptions which result in bias. So what is the simplistic assumption in this model that we are looking at? The simplistic assumption is that the features are linearly dependent.
Yes.
It's a very simplistic assumption. Typically, features are not linearly dependent. So because of that, there's a bias inherent in the system itself. Even before you start, there's a bias. So that bias is characterized by the initial weight, W0. Now, this weighted sum is quite intuitive. And then this bias also is quite intuitive. But the problem is, assume that there's a classification problem. We want to classify whether the tweet is true or false. So it's a classification problem. So there are two classes, true or false. So the two classes have to be modeled by a probability, right? Just like the coin toss, heads or tails is modeled using probability. So the output of this whatever machine learning program should be a probability. So to convert this big number of weighted sum of features into a probability, there is a function called logistic function. It's a sigmoid, one of the sigmoid functions. If you, from math, if you know, sigmoid functions have the shape of S. When you plot a sigmoid function, the shape is that of S. That's why they are called sigmoid functions. And one such sigmoid function is a logistic function, which converts a real number into a number between 0 and 1. So this big number here is not between 0 and 1. We pass it through the sigmoid function called logistic function to get a number between 0 and 1, which is the probability of this particular data item with these features belonging to one class or the other. Right? So this is the essence of the first machine learning algorithm called logistic regression. So logistic regression has logistic function has interesting properties. So let us start with the odds ratio, right? What is the odds ratio? You all know what an odds ratio is, right? It's P by 1 minus P. The odds of raining today, the ratio of the odds of raining today to the odds of not raining today, right? P by 1 minus P. Take the logarithm, log it, L-O-G-I-T, log it, logarithm, we get the logit function, logarithm of P by 1 minus P. And take the inverse of that function. What is the inverse of the function, logarithm function? It's the exponentiation. That is your logistic function. So it has a direct relation to probabilistic features. So logistic function is used as one of the simplistic machine learning algorithms. Okay, I have a lot more slides, but I think I will probably stop here. Are there any questions? Okay, we have 7 more minutes. So I'll probably quickly introduce to us a few more topics using some analogies, because the abstract said that I will talk about some analogies. So the first analogy is how the children learn, right? Children learn in a supervised manner. So parents label everything, whether it is good or bad. Like I had a friend, classmate, whose dad used to label everything for him. Yeah. So he invited us to his home. When we went there, his dad asked a lot of questions. And the final result was, we didn't understand why he was asking those questions. He was basically labeling whether his son's friends are good or bad, whether they can continue friendship with the friends. So that was the intention of calling us to there. So parents have the habit of labeling everything for the children. This is good, this is bad, don't do this, don't do this, do this. So that is supervised way of learning. And the same thing happens in machine learning. So you have a bunch of data which is already labeled for you. You have the data, you have the labels, then you give them to the machine learning model or the algorithm which learns from the data. Then you come up with a prediction. So the prediction could be typically binary. If it is classification, typically the classification is binary, true or false or square or triangle, but it could be multi-class also. There are different ways of dealing with multi-class problems, but typically it is binary classification. And it could also be regression. Regression is when you predict a numerical value, which is a real number, like the price of a house. That's a regression problem. It's a numerical value. So in both cases, whether it is regression with numerical values or classification with a limited number of values, categories, you need labeled data. And then because the data is all labeled, it's called supervised learning, right? So that's the first analogy. So we have the data, which is labeled. And then if you have labeled training data, it is supervised. But generating these annotations or labels is a very expensive process, right? So most of the data we have today is unlabeled, right? So most of the data is unlabeled, but we cannot just ignore the data just because it is unlabeled, right? There's a lot of power in data, right? Information is power, right? Like that, data is power. So when the data labels are missing, we still work with the data. And in that case, we call it unsupervised learning. There's no supervision, no labels. So unlabeled training data implies unsupervised learning. So what can we do with it? We try to determine the latent features in the data, hidden features of the data. And then we can do a bunch of things once we determine the latent features. So an example is students forming groups themselves. One of the first things that the students do without parent supervision is form friends, make friends, right? Form groups of friends. So that is clustering. In one way, it's called clustering of people, right? So in machine learning also, a similar process happens, and that process is called clustering. And that's based on latent features. So we are not going to make friends with others based on the apparent features, like based on the hairstyle or height or weight. We are not going to make friends. We are going to determine the hidden features in the people to make friends, right? That's how the true grouping happens. Same thing in machine learning. The algorithms look for hidden, latent features, not just those columns. Not the columns in the table, but the hidden data inside the columns. And using those latent features, we combine the data together. So I'll illustrate one algorithm, one such algorithm called k-means. So the idea is I will choose the data randomly, or rather, so Gaussian mixture. It's a normally distributed data and normal. So there are three. You can clearly see that there are three groups of data items. So each of these points could be a person, it could be a house, whatever data you are trying to model. Each of those points represent those instances. Now the goal of we have eyes, so we can visualize, clearly see that there are three clusters. But machines do not have eyes. We need to come up with an algorithm which will be able to determine or separate these three clusters. Sorry. So how are we going to do that? So we are going to randomly choose a point here. So there's just one cluster. All the points are in just one cluster, and the center of this point is randomly here. We know that the center is not that, but we can randomly choose one, any point. So add another centroid. So this is the other cluster, randomly chosen. This again is no way the center of the points, but it is random. Because there are three clusters, I will choose third centroid also. I mean, it's not required, but so the third centroid is randomly chosen here. We know very well that it doesn't work, right? This is not the center. But through a number of iterations, so Gaussian mixture, add centroid, third centroid. Now we give the rest, the remaining stuff is done by the program. So through a number of iterations, the centroid is computed each time. Right? Centroid, we all know, is like the center of the data points. So what is the centroid of it? How do you compute the centroid of a triangle? You take the average of the coordinates, right? The same thing if it is 3 points, average of the coordinates. If it is 10 points, also average of the coordinates. We are going to do the same thing to compute the centroid each time. So we keep on doing this. Update centroid, reassign points. Update centroid, reassign points. And at one stage, the points do not move, the centroids do not move. So that results in clustering. So we basically clustered the points into 3 clusters. So that is an example of unsupervised learning. So in unsupervised learning, in clustering, we implicitly identified the latent features. We did not specifically identify, oh, this is a latent feature, that is a latent feature. But can we identify them explicitly? Can we determine the hidden features explicitly? So that can be done using what is called as, one of the ways of doing that is principal component analysis. So principal component analysis is like coming up with a caricature of a person. We all know who the person is, although the picture that we are seeing there does not belong to the person. We know the person, who it is. Why? The reason is because the caricature is, it focuses on the oddities. For instance, the grin of this person in the picture is characteristic. It's unique across all the people, right? The teeth and then the cheek bones. So that is where President Obama varies a lot from all other people, right? So capturing those oddities or those unique features, you're able to pretty much model the person, right, in a caricature. The same thing happens in principal component analysis. On the left-hand side, you see the data points spread in 2 directions, but most of the variation is in this direction. So we can as well keep this direction and get rid of this direction, right? So this is the principal component or the hidden feature. The real features are these x-axis and y-axis. Remember, each point, each item, data item is a point in space. So, and each feature is actually this axis, x-axis, y-axis, and so on. But in principal component analysis, we are going to come up with new axes, which are the hidden features, which cover the most variance. So that is the idea behind principal component analysis. And how do we determine this, the variance? By using what is called as Eigenvectors, right? Eigen in German means characteristic, right? So we are going to get the juice out of the matrix of features, right? So if you have noticed, all the points stretch. They are getting stretched as the points are moving. But the points on these red lines, they don't change. So the points on the red line, they are not changing the direction, right? All other points, they are getting stretched and also changing the direction. But the points on this red line are not changing the direction. The direction is still the red lines. So these points or these vectors are called eigenvectors. This is a simple linear algebra, high school math. So these eigenvectors help us determine the principal components. So these are called eigenfaces. You can apply this eigenvector analysis to faces, and you can actually determine the principal components of faces, images of faces. So you can see that the original image is the top left. And if you, let me show the components first. So these are the components. These are the hidden features of the faces determined using eigenvectors, right? So these are like basis vectors. So this is the first component, second component, third component, and so on of the faces. And then you can generate any face as a linear combination of these faces. So with 10 components, the first 10 components, the face looks like this, 20 components or whatever, 50 components, it looks like this, and so on and so forth. With 100 components, you are pretty much able to regenerate the face. Not exactly, but it is good enough for thing. So that is this is just high school math. Eigenvalues, eigenvectors is just high school math. With just high school math, you're able to do all this interesting stuff. So there's a lot more. So I'll probably, if there's enough interest, I can talk more about these things in a different lecture, a different talk. But for now, because it's over time, let us end here. So any questions? If not, I will end the Zoom session now.